Hola clase. Nosotros empezamos. Hope everyone's doing well. All right, let's get started. Focus my camera first. So this is AP Physics 1. Period 4. Awesome. Okay. Hello. This is Friday, the day before Thanksgiving vacation starts. So I'm super excited to take some days off. I don't know about you. I want you to remember that the assignments from this week aren't due next Friday. They're not due Friday during Thanksgiving vacation. They're due the Friday we return. Okay? So you don't have any homework from me unless you really like physics like I do. I mean, I'm going to study physics over Thanksgiving vacation because I love physics, but you don't have to work on anything from my class over Thanksgiving vacation if you don't want to, okay? I'm a strong believer in the fact that a vacation is a vacation, okay? So do whatever makes you happy in the time that you would be spending studying physics, okay? So let me talk about last time, because we had a pretty significant lesson last time. Last time we learned about the gravitational field, okay? And the gravitational field is really another word for acceleration due to gravity. Okay? And so we learned Newton's law of universal gravitation, okay, which is G. So the gravitational field is G times big M over R squared. So M is the mass of the thing making the gravitational field. Okay? So, and that depends on perspective. So, it's just whatever gravitational field we want to calculate, the mass of the thing making that gravitational field. R is the distance from the center of the mass, okay? So not the distance from the surface of the planet. So for example, the R value for us, if we're considering the gravitational field due to the Earth, the R value for us would be our distance from the center of the Earth, okay? So it's the distance from the center of the mass to the location where you want to calculate the gravitational field. And then big G is a constant of nature. It's called the universal gravitation constant, and its value is 6.7 times 10 to the negative 11 Newton meters squared per kilogram squared. Okay? So that's going to be the same in every problem. the gravitational force is m times g. So we have to keep in mind that there is a difference between what these m's are representing. So this big M is the mass of the thing creating the gravitational field. This little m is the mass of the thing experiencing the gravitational field. Okay? And G is the gravitational field that it experiences. Okay? So these were the two main equations from last time. Okay? I'm trying to think if there's one little point that is a little bit confusing at times is if you're above a planet, if you're up above a planet and say this distance, so here's the surface of the planet, and you have an altitude of r1 and the radius of the planet is r2, then what you would use as big R in the gravitational field equation is going to be r1 plus r2. Okay? All right. So now let's go to new stuff. So here's the scenario. Okay? The scenario is you have a planet or a star, or you have some central body. So this is a central body with mass big M. Okay? And then we are going to consider a circular orbit of a satellite okay, about the central body. So it turns out that not all orbits are circular, okay, but we're going to consider only circular orbits. The math for non-circular orbits is significantly more complicated than for a circular orbit, and it doesn't really add all that much to your understanding of how orbits work. Okay, so we're not going to talk about non-circular orbits. So we have a satellite that is in a circular orbit. Okay, the satellite of mass little m. Okay, so it's orbiting around the central body. We are going to consider the case where the mass of the central body is much, much greater than the mass of the satellite. And this is actually important. It actually turns out that, for example, in the universe, most star systems are binary star systems. So what does that mean? It's actually more common to not just have one sun, but to have two suns in the galaxy. Which you might not have known that, but it's true. Actually, the closest star system to the Earth that's not our own solar system has 3 stars. Okay? So stars tend to have almost the same mass. So what happens if you have two things that have almost the same mass orbiting? Then it's not like no, they're separate. So what happens is if you have two nearly equal mass things, it's like this. It's like they're dancing around each other. Okay. So that's completely different from how the Earth orbits the sun. Because the sun is so much more massive than the Earth, the sun basically stays put while the Earth goes around. Okay. Similarly with the moon is so much less massive than the Earth that the Earth doesn't really move, and the moon just goes around it while the Earth stays put. Okay, so this is important to not have a situation where you have two planets or two stars dancing around each other. By making one of them much more massive than the other, then this one is basically at rest. Okay, and that simplifies the analysis. Interestingly, a couple of years ago, we had a probe that flew by Pluto, and Pluto has a moon that is approximately the same mass as Pluto. Okay, so it's the moon is called Charon, Charon, and Charon is only slightly less massive than Pluto. So as the probe was approaching Pluto, it was taking photos of Pluto, and you could see Pluto and the moon dancing around each other. It was pretty cool. All right. So the Centauri system, which is the closest star system to our own solar system, has 3 stars, and it has 2 approximately equal mass stars orbiting each other, and then a third star that's orbiting around the 2 of those orbiting each other. So it's pretty crazy. All right, so what we're going to do is we're going to do Newton's second law for the satellite. Okay? So Newton's second law for the satellite would be net force equals ma. Now, because it's Newton's second law for the satellite, the mass here is the mass of the satellite. If I did Newton's second law for the central body, this would be big M, okay? The net force is the gravitational force, which is little m times g. Okay. And notice how little m is on both sides of this equation, so it cancels out. Okay. And I'll talk about that in a moment. I'll talk about it right now. The fact that the mass of the satellite cancels out means that no matter the mass of the satellite, if you get it into the same orbit, they're going to have, you could have a really light satellite and a really heavy satellite, and they can both occupy the same orbit and do the orbit in the same way. So if you had a more massive satellite over here, those two satellites are going to complete their orbit in the exact same way. Okay. All right. So the gravitational field is big G, big M over R squared, where R is the distance from the center of the central body to the satellite. Okay. And for the acceleration, because the satellite is moving in a circle, I'm going to use the centripetal acceleration. Okay, which is 4 pi squared r over period squared. All right. So now what I do is I cross multiply. So you have g m t squared equals 4 pi squared r cubed, because you get r squared times r. So this is called Keplers Law, and it is a really useful law for lots of reasons, okay? First of all, what if we know the mass of the star, and what if we know the radius of the orbit? What does that allow us to calculate? It allows us to calculate the period of the orbit, okay? So it allows us to predict how much time is it going to take for the satellite to go around, all right? But actually, the even more useful way to use this equation is because the period of an orbit is fairly easy to determine. What you do is you just watch the thing, right? You look at it through a telescope, and you see this, a moon going around a planet, and you can figure out the period just by watching the orbit, okay? Similarly, by looking at a moon through a telescope, you can see how big the orbit is, so you can determine the radius of the orbit. So if you know the period of the orbit and you know the radius of the orbit, the unknown is the mass of the planet. So you can solve for the mass of the central body. And this is actually how we know things like, what is the mass of Jupiter, okay? Or what is the mass of the sun? How do we know what the mass of the sun is? We can't take the sun and pick it up and set it on a scale and determine its mass, okay? We can't take Jupiter, pick it up, and set it on a scale to determine its mass. So we need some other way that's more indirect to determine the mass. And so how we do that is we watch the satellites. So if we wanted to determine the mass of the sun, we would watch the satellites of the sun, which are the planets, and look at the size of their orbits, look at the period of their orbits, and use those to calculate the mass of the sun, okay? So this is how we know what the mass of the sun is. It's an indirect method of calculation. We know the mass of a planet by looking at its moons, timing their orbital period, looking at the radius of the orbit, and using that to calculate the mass, okay? So the main thing here is we use the satellites to determine the mass of the central body. Okay? So that's really cool. All right? Now you could ask the question, well, what if an astronomical body has no satellites? So the moon, for example, has no satellites. So how could we determine the mass of the moon? Well, actually, we have put satellites around the moon, so that's not exactly true. But, it has no natural satellites. The moon has no natural satellites. So in that case, if it has no satellites, we just have to estimate. We would have to be like, oh, the moon is made out of rock. Rock has a density of blah, and I know the volume of the moon, so I can do density times volume. But that's not terribly accurate because you're having to make estimates about what kind of rock the object is made out of. Okay? Or it could be made out of ice. A lot of moons are mostly ice. So the other thing I want to talk about is the period of an orbit does not depend on the mass of the satellite. Okay? It does not depend on the mass of the satellite. Okay? This is really important. So what it means, and this is where little m canceled out. Okay? So notice how little m is nowhere in the equation here. So The period of the orbit depends on the mass of the central body, but not on the mass of the thing orbiting. So what that means is if you have two satellites that have different masses, and you put them the same distance away from the central body, they will both orbit with the same period. Okay. What would be different is a heavier satellite is more difficult to get into orbit in the first place. It takes more energy to put a heavy satellite into orbit than it does to put a light object into orbit. But once they're in orbit, they have the exact same periods. Okay. So this equation is called Kepler's Second Law. Okay. And Johannes Kepler was an astronomer who basically collected data about Kepler collected data about planets. He collected very accurate data about the motion of planets, and he used the data to come up with this law. Okay, but he didn't know why the law was true. All he did was he said, I'm looking at this data, and this appears to be the relationship between the variables. Okay. So no one knew why this equation was true. And then Isaac Newton came along, and he came up with his equation for gravitational field. And when you use this equation for gravitational field, you can derive, like we just did, the exact same law that Kepler has. So you get what I'm saying? So historically, the way this happened is this law was discovered, and then Newton came up with this equation, which explained why the law was true. Okay? So that was kind of cool. Okay, so so let's do an example. The sun has mass 2 times 10 to the 30th kilograms. Okay. Neptune orbits 30 astronomical units away from the sun. So I'll talk about what an astronomical unit is in just a second. Calculate the period of Neptune's orbit in Earth years. Okay. All right. So what is an astronomical unit? It's usually called an AU. I just called it astronomical units so you know what it stands for. But 1 AU is the sun to Earth distance. Okay. So to say that Neptune orbits 30 AU away from the sun means that Neptune is 30 times as far away from the sun as the Earth is. Okay. So the radius of planets' orbits is most conveniently measured in AU. For example, Mercury has an orbit that is about 1/3 of an AU. Venus has an orbit that's about 2/3 of an AU. I believe Mars is like 1.5 AU. I don't know. I think Jupiter is 8 AU. So the planets have different. So anyways, how large is 1 AU? 1 AU is 1.5 times 10 to the 11th meters. Okay. So let's use Kepler's second law. Okay, and Kepler's second law says G m t squared equals 4 pi squared r cubed. So now I just plug in numbers. So 6.7 times 10 to the negative 11 times the mass of the sun, which is 2 times 10 to the 30th, times the unknown period squared, equals 4 pi squared. Now we wouldn't just put 30 squared because we've got to put it into meters, okay? So we get 30 astronomical units, but 1 astronomical unit is 1.5 times 10 to the 11th, okay? So we have 30 times 1.5 times 10 to the 11th cubed, okay? So I'm going to do this in a little bit more detail. So multiplying these things on the right-hand side out, 6.7 times 10 to the negative 11 times 2 times 10 to the 30th, we get 1.34 times 10 to the 20th t squared equals 4 pi squared, I'm going to multiply all that out. So remember to put this entire scientific notation number in parentheses before you cube it. So that gives 3.6 times 10 to the 39th for the right-hand side. So now I have to divide these two. So t squared equals 3.6 times 10 to the 39th divided by, so now, by the way, now you understand why, have you ever heard that another way of saying that a number is really large is to say it's an astronomical number? Well, this is why. You can see you get really big powers of 10 when you're doing calculations in astrophysics. 1.34 times 10 to the 20th. So we divide those two numbers, okay? Make sure you put the entire scientific notation number in parentheses before you do any divisions. And so that says 2.68 times 10 to the 19th is t squared. Okay? So now I got to take the square root of both sides. All right? So you want to make sure that you put the entire scientific notation number in parentheses when you do the square root. Otherwise, it's going to be bad for you. And I get that the period is 5.1 times 10 to the 9th and this is going to spit it out in seconds. But what I wanted the answer in is Earth years. So it turns out that 1 Earth year is 3.15 times 10 to the 7th seconds. So I have to do a unit conversion at the end here. So 1 year is 3.15 times 10 to the 7th seconds. And that is about 164 Earth years. Okay. So that's just hilarious to me. Okay, so every time Neptune does one orbit around the sun, the Earth does 164 orbits around the sun. So, if we were able to like fast forward time, it would be here's Earth going, and here's Neptune out here going super slow, like that. So that's just crazy to me. Um, and Pluto, which I know is not a planet, but Pluto's orbit is something like 250 years, Earth years. So it's yeah, the scale of that is interesting to me. All right, so one of the things I want to just calculate really briefly, and it's a simple calculation, is what is the velocity, or what is the speed of a circular orbit? Okay. So you might recall that we have we had that equation G equals A. So to determine the speed of a circular orbit, what I will do is I will use the other version of the centripetal acceleration equation, which was v squared over r. And then on the left-hand side, I still have gravitational field. And so see how when we use the second version of the centripetal acceleration equation, which has period, we were able to solve for the period. But if we use the first version of the centripetal acceleration equation, which has velocity, we solve for speed. Okay? So you multiply by r and then take the square root. And what you get is the speed of a circular orbit is square root of the quantity g big M over r. Okay? So what does this say? It says the more massive a central body is, the faster its satellites orbit. And the further the satellites are away from the central body, the slower they orbit. Okay? So part of the reason why Neptune has such a greater orbital period is because since it is further away from the sun than the Earth is, it's orbiting much more slowly. Okay? And furthermore, it's going in a bigger circle, so it just has more distance to cover to complete an orbit. So for both of those reasons, that's why there's such a dramatic difference between the orbital periods. Okay? So I'm not going to do an example with that one. I did want to just talk really briefly about math. So what if I had asked you to solve for the radius of an orbit, the size of an orbit? Okay? You would end up, if you use Keplers Law, see how we have r cubed, all right? So if you were trying to solve for the size of an orbit, you end up with an equation that's like r cubed equals a number. So I just want to make sure that everyone knows how to solve something like that. If you have r cubed equals a number, then the way you solve that is by raising both sides to the 1/3 power. Okay? So r equals number to the 1/3 power. So that's just a little math review to make sure you know how. So that's called the cube root. All right. I did want to really briefly talk about Kepler's other laws. Okay. So Kepler's first law says that orbits are ellipses with the sun at one focus. So an ellipse is basically a an ellipse is basically an oval. Okay. So I'll draw an ellipse. It's a pretty good ellipse, and an ellipse has two foci. So this is a top view of an orbit, by the way. So we're looking down on the top of the orbit. So an ellipse has two foci, which are like maybe here and here. Okay. And the sun is at one of those foci. Okay. And then the satellites go around. So I bet you didn't know that. The sun is not actually in the center of the Earth's orbit. It's actually offset a little bit because the foci are not in the center. Okay. So that's an important point. Now, there's something called the eccentricity of an orbit, which is basically measuring the distance between the two foci. So if you have an orbit that's like a really elongated ellipse, like that, that's called an eccentric orbit. And if you have an orbit that's nearly circular, it's not an eccentric orbit. So the Earth's orbit is an ellipse, but it's an ellipse that is really not eccentric at all. So it's basically indistinguishable from a circle, but it's not quite a circle. Okay? So most of the time, planets' orbits are nearly circular. Okay? So that's why I said we don't really get that much more by the math of an elliptical orbit is much more complicated than the math of a circular orbit. But all the planets have orbits that are nearly circular, so it's like, why go through all of that extra math just to get something that can be approximated as circular? Okay? So, yeah. When is the eccentricity of the orbit really important? Things like comets. So the reason that comets only come by, like Halley's Comet comes by like every 80 years or something. And the reason that we only see the comet every 80 years is because comets have highly eccentric orbits. Okay? And so when the comet is out here, far away from the sun, we can't see it. But when it swings in close to the sun, the surface of the comet melts and it turns into a giant cloud that we can see. All right? So, yeah. And then Kepler had a third law, which says that basically planets orbit fast when close to the sun and slow when far away. All right. So if you have an astronomical body that's in a very eccentric orbit, it'll go fast right here, and it'll go slow when over here. So what happens is it's almost like a dive bomb. So it'll go. You get what I'm saying? So if you have a planet in an eccentric orbit, its speed is changing. The closer it gets to the central body, the faster it starts to go. And then it swings around really quickly, and then it's going really slowly out here. Okay? So that's the content of Kepler's third law. Okay? One other thing I wanted to talk about before I end my lesson just really quickly is a question I often get is, what would happen if the sun turned into a black hole? What would happen to the Earth's orbit if the sun turned into a black hole? And the answer is nothing. Okay? We would be okay if the sun, or our orbit would be okay. The planet would freeze because no more light is hitting the Earth. But as far as our orbit is concerned, we would not fall into the sun if it became a black hole. And the reason is simple. See how the properties of the orbit only depend on the mass of the central body. Okay? So if we take the sun and we don't change its mass, but we compress it into a black hole, we haven't changed its mass. So the properties of our orbit won't change. Okay? What will change is the sun doesn't emit any more light, and so the planet would freeze. So a lot of times people think if we turn the sun into a black hole, that all of a sudden a black hole is going to pull us in. No. So really what's significant about a black hole is not the gravitational field, it's the density that has to be achieved in order to make a black hole in the first place. That's what's most significant about it. All right, so that's my lesson for today. I will see you in